Welcome to this video. We are going to learn about current, resistors, and circuits. We've learned already a little bit about charge. If you take a charge and you put it in an electric field, then the electric field will pull on the charge. The force on this positive charge is directed down because that's where the field lines point. If this were a negative charge, where would the force point? In the opposite direction, opposite the field lines. This force pulls the proton, the charge down, and as a result, it accelerates. So it goes farther and farther as it speeds up. The electric potential energy of the charge converts to kinetic energy because of the acceleration, as it accelerates across this potential difference V. There's a different scenario that we could have, though. Instead of empty space, there can be atoms filling the space, and molecules. When that's the scenario we're dealing with, the charge gets pulled down, and it bumps into the atoms. The electric potential energy is converted to heat because of the collisions. In each collision, the charge transfers some of its energy to the atom or the molecule. And there's a third thing that could happen. Let's say you've got a charge that's moving, and the charge is moving through empty space like this, but there's no electric field. What does the charge do in this case? The key to remember is that if there's no field, then there's nothing pulling on the charge. And so the charge moves at constant velocity because it doesn't feel any net force. There's no field to pull on it. Materials like this, which have molecules that slow down charges, those are called resistors. That's not a very clever name, is it? After all, these molecules resist the motion of the charge. Here's what we can say using fancy physics terms. Resistors impede the flow of charge. Flow of charge is another important concept, because after all, when you have charges moving, there's not usually just one charge. In fact, there are many, and all of these charges are accelerating into and bumping into the molecules. And in physics, the flow of charge has a special name. We call it electric current. Current is given the symbol I, and here's the equation. It's the total amount of charge passing by a point divided by the time it took for that charge to pass by. So if you were to mark like this reference line here, where my mouse is, you could count up how many coulombs pass down by that line per second. And what you're getting is the current. The units for current are equal to the units of charge, coulombs, divided by the units of time, which is seconds. So the unit of current is a coulomb per second, or we call that an ampere, and we abbreviate it capital A. Now here's the thing about resistors. Some resistors impede charge more strongly than other resistors. For example, you could create a bottleneck effect, and that would slow down the resistors. Imagine instead of a wide resistor like this, you have something small. Now you have to cram all of those protons, all of those positive charges, through this tiny narrow space. And as a result of this tiny narrow space that you're squeezing them through, it takes more time for the charge to flow. Resistance is the concept we use which measures how much opposition is there to the flow of charge. In a material like this, the resistance might be a little lower, but in a material that's narrow, the resistance will be higher. The equation for resistance is the potential difference across 2 points divided by I, the current flowing between those 2 points.